Hey students, Mrs. Derby here. Time for our lesson 16 here in Unit 6. Now that we have this idea about how we can start to move some functions around, we're going to look at specifically some trig functions and how we're going to start using these to model situations. Okay, so it starts off with a which one doesn't belong and looking at graph periods. So just a reminder that the period happens, it's how long it takes, how long until it starts to repeat. Okay, so if we're looking at temperature in Muskegon over the course of a year, it probably wouldn't start to repeat until 1 year because we get cold in winter and warm in summer, so the average temperature would have that kind of wave going on up and down throughout the year. So when we look at which one doesn't belong here, maybe we can see always a reason why each graph wouldn't belong for one reason or another. So I might say that this first one I notice, it's the only one not based on pi. Everything else has like a 2 pi and a 4 pi and a 2 pi, so I can tell that one. And it's interesting because this is the only one that has pi in the equation. So sometimes we want to look at the equation too to see what that might be using as we look at that. So this is the only one that has pi in the equation. So that's interesting. Okay. When I look at these other ones, this is the only one that has a 4 going on here. Everything else is just using 2's. I noticed that maybe this graph doesn't belong because it's the only one that's not looking like a sine graph. Remember, sine starts at the center. Everything else is a sine graph. This looks more like a cosine graph. I'm going to put a question mark next to that because my equation clearly shows me it's a sine. So this shifting over seems to have shifted it enough that it looks an awful lot like a cosine graph instead. All right. Anyways, we have a nice way to kind of see what's going on here, and I'm going to come back to this idea in a little bit, that it has a 1/2 in front here, and that has changed it from what was up here, 1 cycle every 2 pi. Now it's taking twice as long, and it's having 1 cycle every 4 pi, twice as long when we compare it to just the sine of theta. Okay, so some neat things going on here that we can start to look at. But let's continue forward. We need to be able to take a look at 16.2 and describe the period from a graph, and then I see that we're going to identify the period from just an equation, and this one goes on to the next page too to start thinking about how we could use it from there. Now that right there is where we're going to see something from our warm-up. Okay, so anyways, let's look at each graph and identify the period. This is going to go pretty quickly because it's just however long it takes until the graph starts to repeat. So this one starts at 0, 0 and continues here. Now you might be saying, well, it hits 0 at this point, but the graph hasn't started to repeat after that. It doesn't go back up again. It continues downward. So the full wave doesn't repeat until right here. And that is happening at 1. So this has a period of 1. Our next one, going a little faster, has a period of 2. This is where it starts to repeat. So it starts here at 0, comes back and starts the next wave of that graph right there at 2. Our next one down has, man, this thing is going through how many cycles? Let's see, 1 cycle, 2 cycles, 3 cycles, 4 cycles in 2 by the time it gets here. Okay, so 1 cycle, the place where it's starting to repeat, would be right here at 2 over 4, or 1/2. Okay, so here the period equals 1/2, or 2/4 if you wanted to keep it in fourths. Working ahead of me, you're probably seeing that the next one has this repetition. Starts up here at 1, dips down, repeats, and returns to 1 at 2/3. So the period equals 2/3. Picking out a period from a graph is pretty easy. Looking at just how long it takes before the pattern starts to repeat. Finding the period from a function might be a little bit more challenging. Okay, but I'm going to use some ideas going on up here. So these ones, to find the period of the function, we could certainly graph it and we could look at that. But we want to be able to also explain what's going on so we're not always stuck with a graphing calculator or looking at decimals. So I want to think about what's going on here. Now, first of all, we have said before that our cosine function, I'm just pulling out my student packet here, cosine of theta looks like this. And so we said before that the period is always happening for our standard cosine function. The period takes 2 pi to get all the way around and to start again. So it's 1 time around the unit circle. Our next guy, thinking about cosine of 3 theta. Well, thinking about what we learned in Unit 5, this 3 is happening inside parentheses. Remember, if you're in my class, that's like bizarro world. Everything's happening opposite of what we think it should be happening. Okay, so this 3 is taking it and not stretching it 3 times wider. We're stretching the period here. We're squishing it, actually. So it goes through 3 full cycles in what would have been the normal period. We're getting it 1/3 as wide. So if our normal cosine goes through, that's not a cosine graph, that's a sine graph. Don't draw that. There's our cosine graph. If our cosine graph normally goes through 1 full cycle in 2 pi, this is telling me it's going to go through a single cycle in 1/3 as much space. So by the time it goes through 2 pi, it has gone through 3 cycles. We can think about that 3 as how many full cycles it's going through. So it's going to go through 1, 2, 3 full cycles in that same amount of pi. So it took that and it squished it to be 1/3 as wide, a single cycle. Well, if it's squishing that 2 pi into 1/3 as wide, we would have a period of 2 pi over 3. Hey there, sorry friends, got interrupted there, but I'm right back here with you, right? Let's take a look at our next one. And again, we're still using that same idea of what we had back from Unit 5. Remember that everything inside the parentheses often happened backwards of what we thought. So a number out front is going to stretch something taller and shorter, exactly like we would expect, exactly like a scalar works. But these ones are inside. These are the C values. And so remember that if they're inside with the angle measure, they're going to work opposite of what we tend to think. Okay? So continuing on, this idea that we would have this time 6 theta in parentheses there means that it's not going to be 1/3 as wide like it was before. This time it's going to be 1/6 as wide as what we would have originally started with. 1/6 as wide as just a regular sine of theta. Okay, and so again, instead of just going through 1 cycle in 2 pi, so thinking about that like it's gone through 1 cycle in 2 pi, this one's going through 6 cycles in 2 pi. And so in that same stretch, just like this one got a 1/3 as small, going through 3 cycles in 2 pi, I don't even know if I can draw something this small. Now this is a sine function, so this is going to start at the origin. And I need to somehow get through 3 full cycles by here and 3 more cycles by there. So we're looking at like 1, 2, 3, 4, 5, 6 full cycles. Whew, made it. So it would take that full 2 pi over 3, that full 2 pi, and divide it into 6 cycles. Now we can do that division, right? 2 pi divided by 6. We can reduce that fraction to 1 pi over 3, or 1/3 of pi. Okay. Now that same way here, I'm going to just do it without even drawing, because at this point I'm trying to squish 10 sine waves in 2 pi. But we can take whatever that is right there. That's how many cycles it's going through if it's inside the parentheses there. We're taking that 2 pi, that would be a single cycle, a single period for cosine of theta, and we're dividing it by 10, which means it's happening every pi over 5 is 1 cycle. Now our last guy here does something a little bit different. Notice this time it's got a fraction in here, and so this 1/3 of theta is going to stretch it 3 times wider. It's going through 1/3 of a cycle in 1 trip around the unit circle. And so this fact that it's going to be 3 times wider, back to our cosine graph, so starting up high and going down low and going up high, by the time it gets to 2 pi, it hasn't even made it through 1 cycle yet. It has only made it through 1/3 of its cycle, so it's going to have gone like that. And it still has lower to go to come all the way back up. Okay, so it's taking this graph and it's stretching it 3 times wider. So its period, if it's only gone through 1/3 of a cycle in 2 pi, we're going to need 3 times that much, 3 times 2 pi to make it through. Okay, or keeping with the same pattern that we've done up here, a period of 2 pi, dividing it by that horizontal scalar, the c value, dividing it by 1/3. Okay, now if you're not sure about that, 2 divided by 1/3, it's the same as copy dot flip-flop, or 2 divided by, in parentheses, 1/3. And there's our confirmation that it is in fact 6. Okay, so 6 pi. Now this problem, or this section, keeps on continuing to the next page, so let's see what else we have going on here. It asks, what is the period of the function y equals cosine theta pi, and explain your reasoning. Well, everything that we were seeing before, the period that we had was the original cosine period, which in this case is 2 pi. Well, in all cases, the regular cosine theta, the period of cosine, is 2 pi. And we need to, what we were doing before is we were dividing it by whatever that c value was. Okay, so in this case, c is pi. So this would have a period of 2. And that brings us back to actually some of the things that we were seeing here. Okay, that we should be seeing this cosine of pi theta should have a period of 2 for a cosine graph. Now, if we want to double check that, we could definitely look at Desmos. We could use a graphing calculator. And I want to find cosine of pi times our angle. I want to double check that I'm in like a window that would take me from negative 2 pi to positive 2 pi. So mine is set like that. You can always set it like 2 pi. And I'm going to go look at the graph. So here's my cosine function. Starts here, repeats by here. With the luxury of drawing on my screen because I know these markers will rub right off. Okay, so there's one sine right there. I'm trying to figure out what it's going to take for it to get back to here. So I'm just going to trace it and just kind of see. I'm going to get kind of close. I'm not going to get exact here, but there I am, pretty darn close to the top of that again, where I'm really close. And you see how close that x coordinate is to 2? There it is. Okay, so a couple ways we could show that. So if I needed to identify a possible equation for a trig function with this graph, well, looks like a cosine graph. It's starting up high, going down low, and then it has a period that is repeating by 1. So we're going to look at maybe a cosine graph. This time the period equals 1. Okay, so I'm going to look up here at my kind of cheat sheet going on here. And if I need the period to be 1, here the period was 2 and I had 2 pi over pi. This time I need the period to be 1, so I've got 2 pi, right, because the cosine period is still the same, over something, whatever that c value is going to be, equals a period of 1. And I have to think about what that would be. Okay, so that's going to be the c value when I write this cosine of something times theta. So 2 divided by something to equal 1, anything divided by the same number divided by itself is 1. So we'd have to have a 2 pi right there, because 2 pi divided by 2 pi equals 1. Okay, and that was our c value. So I'm using the same idea up here. Take our known cosine theta period, divide it by the c, the coefficient in front of the x or the theta, and now I can find the period.